All right, let's share the screen and get going. Welcome to chapter 29. This is the lecture on relativity for the physics class at Philander University, PHS 106. Let's get into it. So I'm going to start out by letting you guys know that this topic, like all others, but probably more so this topic, is a lot deeper than this simple chapter. Relativity itself has a lot of complex mathematics to it. This class isn't necessarily geared towards a high level of mathematics when you enter. So we're going to breeze through a lot of things. A lot of these equations are a lot more complicated. I wanted to get that out to start, like with previous chapters, but this one in particular has a lot of forgetting the word of forgetting the word that describes it best, but a lot of like layman and relativity is something that people talk about that they think they know, but they really don't. I would be an example of don't know. Relativity is not something I'm very strong in because this is very complicated stuff. So a basic understanding of relativity lends itself towards a lot of interesting conclusions to be made, but it is important that you find out your information on these topics from good sources. So if you want to dig deeper into this, use some very basic principles of understanding sources to make sure you get good information. That being said, let's discuss relativity. We're going to talk about these topics. We're going to talk about the postulates of special relativity, the relativity in relation to time, length, addition of velocities, momentum, energy, what a relativistic universe looks like. You know, if we apply these rules to reality, what does that mean? And then general relativity is going to kind of cap this discussion. So, what are the postulates of special relativity? First of all, there's general relativity and special relativity. In this case, special relativity had certain postulates said by Einstein, namely, one, the equivalence of physical laws, meaning the laws of physics are the same in all inertial frames of reference. So if something is working the way it's working, it's going to always kind of work that way. Things don't just randomly happen that outside of the laws of reality. And two, the more interesting proposition here, the constancy of the speed of light. The speed of light in a vacuum is 3 times 10 to the 8th meters per second, 3 to the 8th. C equals 3 to the 8th. Talked about this before. It is the same in all inertial frames of reference, independent of the motion of the source or the receiver. One says when something happens, it's always happening that way because that's just the way it happens. Two says that light breaks rule one. As we all know with relativity, your speed appears to change the speed of things around you. If you're in a car driving down the highway and you pass someone, the car you're passing looks like they're going barely slower than you, even though you're both going around 60 miles an hour. That's relativity. Speed of light doesn't follow those rules. It essentially is the asterisk to rule one. And we'll see why that is the way it is and the math behind it and the factual results of this implication. As well said here, first postulate's very reasonable, but why would speed be constant? It was thought that, like all waves, light propagated as a disturbance in some medium, which was called the aether. That was the prevailing theory as to how light essentially traveled around. This motion through the aether was thought to be detectable by experiments. However, they never found that. The idea being the aether is this stuff that light travels through. And since the Earth rotates around the sun, the Earth should therefore pass through the aether. We should be able to find this out somehow. It should have some sort of wake to it, things of that nature. You should be able to see essentially the relativity I talked about before with the cause. You should be able to see that with the way that the Earth travels through the aether. Because as the Earth is traveling in one direction, if light's traveling in another direction, light should appear at a different speed. However, that's not the case. That the lack of results from aether experiments combined with Einstein, well, being Einstein, along with many other people, ditched this old concept that would have been around for quite a while at this point Instead, special relativity appeared with these postulates. So again, this is sort of what I was talking about before. Water waves, as our measurement of speed, depends on the relative speed of the water wave, right? If you're boating with the current, you're going a lot faster than if you're boating against the current. I'm going to keep saying this over and over again. This stuff is a lot deeper, a lot more interesting than what's going on here. There's plenty of good non-journal-based books on this subject. Lots of very famous scientists have written on this stuff, and a lot better than I can do, right? If this stuff is of interest to you, please look it up. It's fascinating material. So in the previous example, we talked about how essentially the boat speed is dictated by the waves and the boat itself. Light breaks that rule. Light is always going the same speed regardless of how fast you are going compared to it. You're in a rocket ship, so if you're the person down there, you see the speed of light as c. If you're in that rocket ship going 9/10 the speed of light, the speed of light is still c. Speed of light does not slow down even though you're going super fast. And of course, if these were cars driving down the highway, you stand there, see the car goes by at 100 miles an hour. Someone next to the car, on the other part of the road going 90 miles an hour would see the car going 10, right? Light does not work this way. Light is special. Light is distinct from that. The fact that the speed of light is constant also means that nothing can go faster than the speed of light is the ultimate speed limit of the universe. The implications of that relate to what we're going to be talking about in a bit, how that actually functions in that way. So, the relativity of time and time dilation. To begin to understand the implications of relativity, we can consider a light clock. What that is shown here below, in that if you shoot some light out of S, it'll travel a distance and return to the sensor D. Since you know the speed of light and you know the distance, you can figure out the time it takes, right? Easy enough. It says V equals D divided by, T equals D divided by V here, right? Very basic stuff. But what happens if we take this same concept and we move it? What happens at that point? Well, what we see here is that the total distance of light travel has changed. The light has taken a longer trip than before. Since it takes a longer trip, it therefore takes a longer trip, right? Does that mean its speed is different? Well, the light has traveled further, so now the round trip is a different equation here, when we need to take into account the fact that we have triangles, right? Everyone loves their triangles. So, therefore, the moving clock appears to run more slowly because the light has a longer trip to take. The light isn't just bouncing there and back again in a straight line. It's going across this triangle. The speed of the light is the same in this image, but the trip the light takes is longer. Therefore, the clock doesn't see the light come back as quickly. So what you need to do is you need to take into account this triangle that's formed by the light, which is the denominator shown here. Previously, in the straight line, the denominator was just, right, the velocity. Now the velocity is taken into account this triangle motion, which is shown here. I hope that makes sense. Again, I suggest, as I've always suggested, if this doesn't make sense, find some reputable source on YouTube, a Khan Academy, something like that. Watch a video. They can maybe do a better example. They have images. They can devote the entirety of a conversation to this one topic. As the speed gets closer and closer to the speed of light, the clock runs slower and slower and slower. And we can see it's a logistic growth here, right? Once you hit about like 0.8, the bar shoots straight up. This result applies to any kind of clock or process that is time dependent, right? What's not time dependent? If it did not, the first postulate would be violated. Since this works with things in time, anything that has to do with time, so read anything, follows these principles. So let's define a couple things before we go forward. Event. Event is a physical occurrence that happens at a specific location at a specific time. An event is, well, an event. You snap your fingers, that's an event. Proper time is the amount of time separating the two events that occur at the same location. You have proper time kind of gets into this time dilation conversation that we're having. What is proper time? Time dilation is something that, funny enough, actually has been measured. This idea of clocks slowing down is, in fact, a true statement. Time dilation has been measured with extremely accurate atomic clocks on planes. It's also frequently observed in subatomic particles. Funny enough, if you Google it, you will find an example of someone that took two identical clocks, one to the top of a mountain and one, I think a high school teacher took a clock to the top of a mountain and his class kept the clock down below, and the clocks went out of sync according to this exact argument here, this idea of time dilation. Now, the consequence of time dilation is that different observers will disagree about the simultaneity of events occurring at different places. In concept, this is, since time is the thing that's being changed, since light is taking longer to do the same thing. Light is traveling a longer distance while it travels arguably the same distance. Two things that appear to be the same actually aren't. So let's go over length contraction here. It's a similar concept, but sort of backwards. So you are in a space shuttle. You are heading towards the star Vega. Observers on Earth see the astronaut's clock running slowly. It takes him 25.6 years to go from Earth to Vega. But for the astronaut, it took him 3.61 years. How is this possible? How can a 25.3 light year long journey, 25.3 year long journey, only take 3.61 years? Is this some Dragon Ball Z math going on here? Well, technically, yes. Right? A way to visualize this concept is the idea of switching your inertial frame. So, how does it appear the astronaut who thinks his clock is fine? He sees the distance as contracting for him, meaning for the astronaut, Earth is flying away from him at 0.99, and Vega is flying towards him at 0.99. So he sees Vega coming to him in 3.57 years. What happens here is you get a change in proper length. Proper length is being defined as the proper length is, I'll just read the sentence, the distance between 2 points as measured by an observer who is at rest with respect to them. So the proper length, how far is Vega away from Earth? 25.3 years. But since you are traveling at a speed that you need to care about the speed of light, you need to describe it with the speed of light, as in 0.9 c, right? The length that actually appears to go down changes. By that I mean, you got to think it takes 25.6 years for the light from Vega to get to Earth. So if you're traveling 0.9, you're essentially keeping up with the light. And since light defines time, as we talked about before, that triangle, that light clock, time itself is going differently, and distance is related to time and velocity as shown before, so distance will change too, according to this equation here. Again, I'm going to keep saying this stuff is far deeper than I can cover in a single slideshow, right? If this is of all interest to you, please do some reading, go find a reputable source of this material. Point of all this, length contracts according to velocity, meaning the faster you go, the shorter you become. Did I skip something? I did, yeah, here we go. Important note here is that the direction you're going is the length that is contracted. So this astronaut here in this reclined chair for some reason delta x would be the only one change. See, x turns to delta x. Y would not change. What does that mean? Funny enough, he stands up a bit. He gets a bit shorter and he stands up a bit more. Because he's going so fast, these physical events change. But do they change with respect to him? No, they change with respect to the observer on Earth. Weird, huh? So, relativistic addition of velocities. We talked about velocity addition before. We talked about it back in Physics 105. The example of the two cars driving on the highway. What are the relativistic velocities? Pretty easy stuff, right? Well, what do we do when we have to deal with light? So, suppose two spaceships are heading towards each other, each with a speed of 0.6 c with respect to Earth. How fast do the astronauts in one ship see the astronaut in the other ship approach? Well, according to the previous physics we've done, add them together, 0.6 plus 0.6, 0.12. Well, now you're going faster than the speed of light. We have an issue here, right? So what we have to do is have to take into account the relativistic speeds in relation to light, and we get a new equation that is much grosser looking, shown here. Essentially, wherein we take c into consideration. So we take those maths and we put them into this equation. We find out that the relativistic speed, the speed of the incoming ship, is actually 0.88 c. You're faster than the 0.6 that a passive observer on the side would see, but you're not straight up the addition of 0.6 and 0.6. The faster you go, the more relativistic velocity flattens out, because you can't break the speed of light because of the laws of relativity. This is a big subject. I keep having to pause here because this is a conversation that's best done in person, or best done with lots of visual examples that we simply don't have the time for here. Please, if this stuff is of interest, look it up. Google relativistic addition of velocities. Watch a couple quality source videos on that. It's cool stuff. However, the point of this class is to give you a brief introduction and to show you the equations, and the equations really aren't that hard if you follow your knowns, right? So we're talking about relativistic velocity. Relativistic momentum follows more or less the same idea, just now we include mass in the conversation, right? All energy and momentum conserved when you do all this ridiculousness? Well, the answer is that momentum is no longer given by mass times velocity. Instead, again, you got to throw c into the mix. You got to consider the triangle that we talked about before of the path of the light and all the other ridiculousness that goes on in this high-level mathematics. And as I keep going forward, keep in mind, we have experimental data showing this stuff to be accurate. These clocks do change. These lengths do actually change. It's crazy. What we notice here is with classical momentum, as the faster you go, well, momentum is related directly to velocity, so it would be a one-to-one, but momentum increases exponentially as you get closer and closer to the speed of light. That leads us directly into probably the most famous equation of mathematics, E equals mc squared. If the momentum increases without limit, the energy must increase without limit as well, meaning the relativistic energy of something is equal to its momentum, right? And if we chop out that bottom bit there, we get E equals mc squared. Well, the rest energy of anything, something's at rest, right? The rest energy of everything is equal to its mass times the velocity of light squared. Right? Put v equals 0, 1 minus 0 is 1, square root of 1 is 1, no denominator. So the rest energy of ordinary objects is absolutely stupid, right? It's immense. Nuclear reactions, only a fraction of a percentage of the mass of the fuel becomes kinetic energy. But even that is enough to create an enormous amount of energy, right? Every elementary particle, such as electrons, has an antiparticle with the same mass but opposite charge. this is a huge conversation. There are so many subatomic particles out there. It's crazy. The interaction with each other are really cool. Again, look up positron. Watch a video on YouTube from a reputable source on it. It's pretty sweet stuff. A positron is, well, an electron with the opposite charge. So the mass is the same, but instead of 1.6 times 10 to the negative 19th as a negative charge, it's now a positive charge. So when an electron and a positron collide, they completely annihilate each other. The actual masses are gone, and what's emitted instead is gamma ray radiation. The mass turns into energy, right? And the amount of energy released by these is given by E equals mc squared. So you can figure out the energy it had before, the potential energy essentially. And this equation here, again, is throw C into our kinetic energy equation, right? You can figure out how much energy is released by these positrons, and this math ends up being correct when we do these sort of experiments. CERN, the Large Hadron Collider over in Switzerland, I believe. What is it? It's basically a big particle shotgun. It shoots lots of particles straight into each other so that when something happens, we can accurately measure the results and verify these equations and break them open to see what's inside, but that's another thing. At ordinary speeds, relativistic kinetic energy and classic kinetic energy are indistinguishable. Notice down there at the bottom, basically the same number. However, relativistic spikes up the faster and faster you get because you need to take into account the weirdness of light. At this point, I'm going to have to interject here and say the weird thing about relativity is it doesn't actually change everything we've done prior. All the old physics, Newton's laws, F equals ma, all that stuff are true because we don't deal with anything relatively close to the speed of light at all, ever. And all these equations, C is such a stupidly huge number that it basically boils down to zero. The relativistic part of day-to-day life is essentially meaningless. The change is so many places past the decimal point that you don't actually see the actual difference. You cannot sense the actual difference between relativistic and classical physics at sublight speeds, essentially, at speeds far below C. Once you get up to C, you need to realize that things warp and change really weirdly, causing things to happen. If you haven't seen Interstellar, Interstellar does a not bad job of describing this while being a good movie. I'm not going to say many other movies do as good a job as Interstellar. Yes, Interstellar has its flaws, of course. If it was honest, it'd probably be a really boring movie, right? So, it may seem as though relativity has nothing to do with our daily lives. That's not true. That's very, very not true, right? Medicine makes use of radioactive materials for imaging and treatment. Most of you as the bio majors will understand that. Satellites use these relativistic effects to account for functioning. The satellites are moving fast enough and are far enough away that you actually need to take this stuff into account in order to properly track and transmit data. Space exploration would... space obviously is a big part of this. You want to travel long distance, you go really fast. You need to take these things into account. I said before prior that the example of a high school teacher climbing a mountain and noticing the clocks are off, right? That's some dude did it and was able to show this difference. Why I keep referencing the mountain? Well, when we get into general relativity here, the important thing to think about, one of the important concepts Einstein is credited for, Einstein worked with other people, by the way, he wasn't a island into himself, is that you need to visualize the difference between gravitation and acceleration in the sense that within a closed system, you can't tell the difference. If you drop a ball on Earth, it falls. If you are in a place without gravity, flying in a certain direction, and you drop a ball, it falls. This is, right, simulated gravity, fake gravity. You can't tell the difference of what's causing the force. You only see the force happening. So this leads us to a principle that's called equivalence. All physical experiments conducted in a uniform gravitational field and in an accelerated frame of reference give identical results. Since it doesn't matter what the force comes from, it only matters how the force is interacting with you, you can essentially argue that if I see a force act this way, I know this will produce that force, therefore that force was produced by this. Sort of a sort of an egg before the chicken argument. Therefore, the people in the elevator on the previous page, these people in these elevators, cannot, unless they're able to see outside the elevator, tell if they're in a gravitational field or uniformly accelerating. Lady on the left here, with her hand in her pocket for some reason, isn't moving. The ball falls because of gravity. Guy on the right here, with his fancy red shirt, is not in gravity. Instead, the elevator is shot into space. But the ball acts the exact same because the elevator in space is traveling 9.81 meters per second in that direction, and gravity on the lady here is pulling down 9.81 meters per second. When the elevator is moving at a constant speed, the light from the flashlight travels in a straight line. Cool. But if the elevator accelerates, the light bends. This is because, again, light takes time to reach something. And if the elevator is moving, the light on the right here in B, when the light hits the elevator, that is the distance the elevator moved, the elevator accelerated in that amount of time. Since you can't tell when you're inside the elevator if the elevator is moving or the elevator is not moving, you only see the results. We can use this idea of equivalence to describe how gravity affects things, right? Principle of equivalence tells us that the light should bend in the gravitational field as well, and lo and behold, it does, right? This gravitational bending of light can be observed during a solar eclipse. When stars appearing very close to the sun can be seen. This is ridiculous. First of all, don't stare at eclipses. Secondly, on a normal day, the sun will block out certain stars, right? You can't see through the sun to see a star, but during eclipse at that time, the light from that star, since the sun is dimmed by the eclipse, the light bends around the sun due to the sun being massive, having a lot of gravity, and you actually can see stuff behind suns. If you, again, watch Interstellar when they have that image of the black hole, the reason the black hole looks that way is because of gravity bending light. Watch a video on it on YouTube if you want to get more in depth about this topic, but it is amazing that you are kind of able to see all sides of a black hole from all parts, from all positions looking at the black hole. It's crazy nut stuff. But essentially all this is boiling down to is that gravity exhibits a force on everything. And since light can have force exhibited on it, gravity works against light and, well, as I said, everything. If the gravitational field is strong enough, light may be bent in such a way that it cannot escape, creating a black hole. That's what I said about forward interstellar. Calculations show that the radius of a black hole can be given by its mass. Black holes, funny enough, are not massive objects. They're very dense objects. We think we found black holes that are the size of, pin needles and stuff like that. But they distort light around them still because they're super, super, super dense. Sure, we have the Great Attractor in the center of a galaxy. It's a massive black hole, has a massive mass to it, therefore massive density, therefore collecting lots of light, and the entire galaxy is being attracted towards it. But you have miniature black holes popping up all over the place. Look it up. It's super, super weird, right? Plugging in the numbers show us that Earth would have a radius of about 0.9 centimeters if it was a black hole. If you take Earth's mass and you bring it down to a circle that's less than a centimeter across, less than half an inch across, you can create technically a black hole because it's the density that you care about. A way to visualize this would be this classic example here. The bending of light around a massive object in this image is space itself being bent. If you've ever been to the mall, you've played that game where you flick a penny, it goes around the circle, eventually falls down. You can consider space, which is physical reality, and time, which is, I guess you could say, light moving across space, to exhibit this way. And a black hole is essentially a point to where the light can't bend itself out. I really wish I could go into greater detail, but I got to keep the train moving very fast, pun not intended, in this class. So I got to skip over a lot of super in-depth stuff. Each of these chapters is a class in and of itself, right? If this stuff is of interest to you beyond simply getting a good grade on the assignment and the test, look it up yourself. Find out more information. This is a really cool subject. If you haven't seen Interstellar, I suggest you watch it. They do a very, I would argue, a pretty good job of going into detail about this stuff. So, summary of chapter 29. Let's summarize special relativity, shall we? The laws of physics are all the same in all inertial frames of reference. If something's happening, well, that's because it's happening, right? However, the speed of light in a vacuum is the same in all inertial frames of reference, independent of the motion of the source or the receiver. So, the speed of light does its own thing. We have equations that explain concepts of reality in relation to the speed of light not changing in a vacuum, such as this equation shown down below, which shows you how clocks will work given this weirdness of light. These equations here show how length changes. Again, length along the axis that the light is traveling. That the object is traveling. How you add velocities, again, given c. Basically, you shove speed of light c into your equations from last semester, and then they become these things. Momentum and energy, of course, relate in these same methods. Since you're changing time and you're changing distance, you're changing, therefore, velocity, momentum, and energy, right? Equals mc squared is actually a definition of rest energy. And then kinetic energy, potential energy, not really. And then kinetic energy then can relate to equals mc squared, as shown here. And the last weird part to talk about is, if you don't know what's causing the force, you don't know what's causing the force, funny enough. That was brutal. Brutally interesting, I hope. This stuff is a massive, massive endeavor to understand. I hope things went well for you. Good luck on your homework. If you have any questions, feel free to comment down below. If you have any, if you need a recommendation as to how to dig deeper in this stuff, feel free to dig deeper. That will be the end of this lecture. We will have one more this year in spring 2020. We have one more online Zoom lecture. I'll post them on YouTube as usual, and stay safe out there.